This lecture is more about organizational techniques, and we'll introduce the use of the math class. Now that we have an understanding of methods and their reuse, you might be asking, what if a max method needs to take two doubles or a double and an integer? The max method we developed takes two integers and returns an integer. Well, that's the role of overloading. Designing methods with the same name but a different signature. I've mentioned scope a few times in the past couple of weeks. Scope defines where a variable can be referenced or used. It's time to get a better understanding of scope. The math class we've used to raise a number to a power and to generate a random number. We'll take a closer look at some of the more common math class methods and discuss accessing the Java API for further documentation. The Java API stands for Application Program Interface. Then we'll have some discussion about abstraction. Understanding that we only need to know how to use a method, and we don't need to know how the method code is implemented. Again, the Java API is a good source of examples of abstraction. And finally, as you become more challenged to write more complex programs, you need to follow a design paradigm that makes your job of implementing a solution less time-consuming with fewer errors, and it produces the correct results. If you remember, for the max method in the last lecture looked something like this. Its signature returns an integer, and it's expecting two integers as its formal parameter. Now, take a look at this second max method. The body is the same as the first. The only thing that differs is the signature. Both of these methods can exist in the same class. The Java virtual machine sorts out which one to use based on its actual parameters. With this call invocation, the Java virtual machine sees that two integer values are being used as actual parameters, so the max int will be used. Now with this call invocation, the Java virtual machine sees that two double values are being used as actual parameters, so the max double method will be used. These two small examples demonstrate the concept of overloading. The next couple of slides will look at overloading again. In examples 1 and 2 above, it should be pretty clear and straightforward which methods the Java virtual machine will use. Example 1 will use method 1, and example 2 will use method 2. But what about example 3? Its actual parameters don't match any signatures exactly. The Java virtual machine, though, is smart enough to understand that an integer can be implicitly cast as a double. So consequently, method 2 will be used. Well, sometimes there may be two or more possible matches for a particular invocation of a method, but the compiler can't determine the most specific match. This is referred to as ambiguous invocation. Ambiguous invocation causes a compile error. Now we have a problem. The compiler can't sort out which of the two methods' signatures match the invocation. Consequently, it throws an error. Take a look at the system.out.print line. It's passing two integers, but the signatures for max method 1 says, well, I want an integer and then a double, and max method 2 says, well, I want a double and then an integer. And even though an integer can be cast as a double, the compiler gets really confused. There's a copy of this program on Blackboard if you care to compile it to see that the compiler will throw an error. scope is that part of a program where a variable can be referenced. The scope of a local variable starts from its declaration and continues to the end of the block that contains the variable. A local variable must be declared before it can be used. In the example of the max method, num1 and num2 and result are local variables and are only known to the method max. Since these are local variables, they cannot be accessed anywhere else except inside the method. And each time the method is started, the variables are created new. They do not retain any values from one invocation to the next. And once the method ends, the variables are released from the memory stack. You can declare a local variable with the same name multiple times as long as they are in different non-nested blocks of code. But you cannot declare a local variable twice within a nest. In the case above, we have three variables named the same. The red ones are known to the main method, while the green ones are known to max. There's no conflict or confusion with the names, and there are 6 distinct variables. This type of coding is very confusing and is a sign of unprofessional programming style. Try to keep your names unique to the methods. Well, you need to watch how you nest your declarations. In the red code on the left, I is created and destroyed in the first for loop before it is declared again in the second for loop. However, in the green code, I is already declared as having the scope of the entire method. Consequently, trying to declare it again inside the body of the if statement, for example, will throw a compiler error. Well, a variable declared in the initial action part of a for loop header has as its scope the entire loop. So I is available throughout the entire loop body. But a variable declared inside a for loop body, J for example, has its scope limited to the loop body outlined by the red braces, from its declaration to the end of the block that contains the variable. So what does this loop produce? Well, stop the video and try it in TextPad. Well, the output will be that the value of I is displayed from 1 to 9, while the value of J is always displayed as 1. Why? Well, every time the loop exits at the end of the loop, before it returns to the for statement to increment I and test to see if the loop should be executed again, the stack for the loop body is cleared. So J is destroyed, and it is created again the next time the loop body is executed. Well, just as a note, this will not work either. The first I is known from the opening and the closing of red braces within the red for loop. Trying to declare it again in the green for loop will throw a compiler error. So when nesting counter control loops, the best practice is to use different variables to control each loop. Replace I with J in the green loop and all is well. Well, think of these circles as enclosing blocks of code, nested. Okay? Well, the red block of code can see and use X, Y, and Z, while the yellow block of code can see X and Y, but it can't see Z. And the blue block of code can see and use only X. It can't see or use Y and Z. The idea of abstraction is that you can drive or use a car without having to know all its inner workings. You trust if you step on the gas pedal, the car will move forward, hopefully. You do not know or need to know about the pistons, the crankshafts, the drive shafts, the axles, or how they all work in order to drive a car. Well, the same is true about methods. The gas pedal in this case is the signature. If you give the method the right inputs, gas, it will give you the right results. It'll move the car forward. Think of the method body as a black box, the pistons, crankshafts, etc., that contains the detailed implementation, the code of the method, which you don't need to know about in order to use the method, drive the car successfully. So think about that as a black box. When we develop a modular solution to a problem, okay, we specify what to do, but not how to do it. We call this procedural abstraction. So when designing methods as part of a solution, we specify each method at design time before actually implementing it. This separates the purpose of a method from its implementation. Information hiding is simply the idea that you will need to use methods written by others without knowing their algorithms or their code. This is the details of their implementation, and it's hidden. For example, using the Java API math.pow method, you didn't need to know how the power method did its work, just that if you gave it the correct actual parameter, it would compute the power of the number you wanted. Well, we've kind of heard this before. I've talked about the benefits of methods and modules. We only need to write a method once, and we can reuse it. We can reuse it in our programs. Other people can use our methods in their programs, such as the math.pow. Many people have used that method just in this class. Information hiding, as we just talked about, hides that implementation from the user. The user doesn't need to know how the code was written to implement the method. They just need to know how to use the method. We just need to know how to drive the car. We don't need to know how to fix the car. And finally, by using methods, we reduce the complexity of our programs. We can take a large problem and break it down into many smaller problems, each one of which is easy to resolve. The Java API provides an interface to a set of utility classes and methods that you can use to write your Java programs. API stands for Application Program Interface, and it is the professional Java programmer's best friend. Not only does Oracle provide hundreds of APIs and methods, third-party vendors also provide specialized APIs, from accessing databases to implementing maybe specialized drawing tools. The page above is a snapshot of the Java API, and in particular, I wanted to show the familiar scanner class. The sample code in the green bracket should be somewhat familiar. In the orange bracket, the code shows how to set up the scanner for getting data from a file. And that's for another lesson. But be aware, in order to use most of the classes or methods, the class must or will need to be imported first. Stop the video and browse the API a little. The link is at the bottom of the screen. Well, let's take a quick look at the math class and what it has to offer. First, you'll see that there's a couple of constants, pi and e. Make note on how they are referenced. Perhaps you might want to resurrect your early program where we calculated the area of a circle and replace your constant value for pi with the math class pi. We see a large number of mathematical methods, trigonometry, exponents, etc. This should make all our math ed majors very happy. Let's take a look at a few of these methods that you might find useful in your programming. Well, again, here's a quick quick snapshot from a couple of pages of the Java API. Make note that there are 4 max methods and 4 min methods. Good examples of overloading. A lesson you might take away from all of this is before you develop some complex code, check to see if it's already been developed. Check the API. Don't reinvent the wheel. Let's take a look at a couple of methods that are classified as exponent methods. These are just a few of them. The exponent method, EXP, may be useful when doing some complex financial calculations. Square root is easy to use, but we can accomplish the same thing with POW using a fractional power for b. Well, as we can see, there are several different rounding methods: ceil, floor, rent, round. Right? Rent is probably the most balanced rounding mechanism. Notice it'll round up or down depending on whether the end result will be even or odd. Round, simply returns an integer, and the rest return doubles. So take a moment and study these examples. Well, we've seen earlier that min and max are overloaded methods that can be used with either integer type or floating point type data. The Java API will come in handy when trying to understand the formal parameters a method uses as well as the return type. Well, we've already used the random method a couple of times, but sometimes we want to generate a random integer between 2 values. Well, the first example generates an integer between 0 and 9. We've done this. Note that the multiplier is 1 more than the maximum integer we want to generate. The second example generates an integer between 50 and 99. Let's take it apart. The int rand times 50 will generate an integer between 0 and 49. Then by simply adding 50 gives us between 50 and 99. Well, Java has this ability to treat a character data type as if it were a byte, an 8-bit number, since characters are 8-bit. And if we look at our lowercase characters, a, lowercase a, it has a numeric value of 97. That's what its bits would equate to. And a z has a numeric value of 122. So if we look at the red code will generate a random number between 97 if int math random is 0, and of 122 if math random generates 0.999 something. So consequently, casting all of that then as a character would give us a random character between lowercase a and up lowercase z. So we have a little generalization formula where we use ch1 and ch2, where ch1 is the lower character, lowercase a, that we want to use, for example. And ch2 is our ending character, our upper bound, z. Right? And since we're dealing with characters that can be treated as bytes, we do mathematics, or we can subtract them and add to them, etc. So let's take a look at the example. Well, the first example is a restatement of our example to generate a character between lowercase a and lowercase z. And remember that characters have single quotes. Now our second example here will generate a character between n and t. So it might come in handy sometime. Well, after our little discussion of how to generate a random character, the author presents a clever way of using a generalized function, getRandomCharacter, to the problem of generating several different kinds of random characters. So we see the implementation of getRandomCharacter at the top of the slide. Now, although the author's code is elegant and meant to demonstrate that a method can be called by other methods to accomplish the same task, the getRandomCharacter method can be invoked directly with any given set of parameters without going through the intermediate methods. You can follow along in section 12 of your text. It has a complete discussion of the design approach and the top-down implementation for this print calendar problem. Well, the concept of abstraction can be applied to our process of designing and developing programs in a stepwise manner. When writing a large program, we use the divide and conquer strategy, also known as stepwise refinement. We decompose a large problem into smaller subproblems or modules, and then we further decompose these subproblems into smaller, more manageable modules. We continue to decompose until we have identified a set of small problem solutions, small modules that are complete in that when taken together, they solve the problem. They are cohesive in that each small module solves only one problem. And they are coupled. That is, modules are interconnected only by the data that they pass back and forth. The implementation or the code may change between modules, but the change doesn't affect the implementation of any other module. So let's take a look at designing a program to print a calendar. And during design time, we continually ask the question, what needs to be done? We're not concerned with about how it's done. That's an implementation issue. So you don't need to know any programming to design a solution. So from here on out, we're going to take a look at designing this program that will display a calendar of a given month for a given year. We'll go through the design process, and then we'll also look at the implementation process. During design time, we use what is known as a structure chart. We use it to design a solution to our problem, and it's much like the organization chart in a business. The upper boxes are management, and they control or tell the lower boxes to do some work. In designing a solution to our print calendar problem, the first questions we should ask are, well, what do we need to know? What is the input? And what do we need to do with it? So we have two boxes, modules, read input, and print month. Read input is well defined. It does one thing. It doesn't need any further refinement, so we don't have to break that down into a smaller problem. But this print month, what needs to be done? Well, we need to print a title, and we need to print a body. Let's ask some more questions. Well, what do I need to print the title? It gives us, well, you need to get the month. Well, after knowing the month, what is needed to print the body? Well, you know, the answers to those questions, we need a start day and we need a number of days. And so those become, answers to our questions become the lower modules. Well, all months start with 1. We don't have a problem there. However, in order to get the end of the month, the program needs to determine the number of days in a month. And finally, we have to determine if it's leap year, in case the month was February. So note in our final design, the top module, print calendar, is our main. The main will invoke read input, or read input may be implemented in main, and it will invoke print month. Print month, in turn, will invoke print month title and print month body. And we continue down the design. Designs like this are read top to bottom, left to right. So a left branch must be completed before its work can be moved on to the branch on the right. So I've numbered these to kind of give an idea or a sense of what will be happening when we execute. Main, number 2 will do read input. Then we'll do number 3, print the month. Well, it has to get the month title and get the month name before it can print the month body, which has to get the start date, etc., etc. So just the numbers are my way of kind of indicating the order of execution. These do not have to be the order in which the program is implemented. A top-down approach to implementation is to implement one method at a time from the structure chart, beginning with the top and proceeding to the bottom. Stub methods can be used for methods waiting to be implemented. A stub is simply an incomplete version of a method. It can simply be the method's signature with the return of some simple value or a message that is displayed. The use of stubs enable us to test the upper methods, the invoking methods. Let's implement the main method first, and then use a stub for print method. For example, let print method display the year and the month in the stub. Thus, your program may begin to look like this. We use stepwise development and testing. That is, write a method and test it. Then write another method and test it. The slide shows we've written our main method, and in order to test it, we need a stub method called print month. Print month is not fully implemented. All we need is something to tell us that we got to the method, and it recognizes our calling parameters. So we temporarily implement print month with a system.out statement. Run the program, make sure print month has displayed the right information, and we can check main off our list. It is fully developed and tested. No more worries. We can move on now to developing and testing print month. Well, checking back at our structure chart, main and read input are complete. We now need to move to developing print month. You see the implementation above. We only need to be sure that the stub methods, print month title and print month body, exists before we can test print month. And then it's done and tested. We continue our incremental development and testing until we have completed all our modules. This process speeds program development. It requires that we only need to debug the latest module we've developed, and all the earlier modules have already been tested and debugged. So our next step, implement print title, test, and then implement print month body, test, and so on. Well, the next few slides we'll look at will step through our implementation of this print calendar. So feel free to stop the video and study as we go along. Well, one thing to notice as you study this implementation process is how those early methods, the ones towards the top of this structure chart, don't do much work. That's left to the later methods. As we move to the lower methods to the bottom of the structure chart, this is where most of the work is done. Notice how print month title uses get month name, which in our analogy to a business is on the bottom of the structure chart. It is a worker bee, and it doesn't tell anyone else to do its work. Just as you can implement your design in a top-down manner, you can choose to use bottom-up. The bottom-up approach is to implement one method in the structure chart at a time, starting at the bottom and moving towards the top. For each method you implement, you need to write a little test program to test it. Both top-down and bottom-up methods are fine. Both approaches the implementation of the methods incrementally and help isolate programming errors and make debugging easier. Both end up with a program where the methods are complete. That means taken together, they solve the whole problem. Cohesive, each method is only responsible for completing one task. And coupled, they are loosely coupled together by the data they exchange. And each method's implementation is independent of any other method's implementation.